Good, so let's go over some stuff. Anything's fair game for the exam, so let's first talk about non-programming stuff, and then we'll talk more about Python this lecture, and then for the rest of Wednesday's lecture. So let's talk about non-programming stuff that you might need to write about. So let's go back to our ethical theories from the beginning of the semester. Let's go back through them so that we all have them fresh in our minds. So first was Kantianism, right? And Kantianism is an ethical theory. We're studying ethics in this class. And what is ethics but trying to figure out when some concept is good or okay or the best thing to do. So when you have some decision to make, ethics is a way to frame that decision and come up with a good answer to it, right? So upload failed. Really? Well, I'll figure that out later, I guess. But, all right. The first kind of ethical theory is Kantianism, and what Kant thought was that you should always obey that golden rule, act in a way that you want everyone else to always act. Okay, that word always, that was so important when we talked about Kantianism. What it means is that there is no special exceptions for you. You can't lie just this once. No, you always have to follow these rules. No special exceptions. No hypocrisy. You always got to do the right thing. Okay? Kant thought that it was also, that idea was also equivalent to not treating people as a means to an end, like a way to get something done. You should treat people as humans. You want to be nice to them. Act in a way you want everyone else to always act towards you. Okay? So he thought that these two bullets were equivalent, and if you take a philosophy class, maybe you will study examples of Kantianism and how we could use Kantianism to determine the right thing to do, to frame an ethical dilemma. So the first example is lying. What would Kant say about this? Kant would be very much against lying, right? You don't want to be lied to. You should never lie. He would ask, would I want someone else to always lie? No. You always want them to tell the truth. Kant would say that lying is bad. You should never do it. But I think you can think of some cases where lying is a good idea, right? Maybe a murderer comes to your house and says that they want to kill your friend, and you should probably lie in that situation to tell them where your friend really is not there, right? Something like that, or lie to your kids about Santa Claus or something. It's okay to lie sometimes. Most people would want to lie in certain situations, but Kant would say no. Okay? That's the idea. So that's one example. Another example would be stealing. Kant would again say that you could never steal. Ask the question, should everyone always steal? And no, I think that's a bad idea, right? You wouldn't want everybody to always be going around stealing stuff. So Kant would say, no one should ever steal. And you can also think of situations where it might be a great idea to steal. Like if you have nothing and you need to feed your family, you're going to want to steal, and maybe that's the best thing for you, at least to stay alive. Kant would say no to that. He would say, no, find another way to get food. That's not okay. So, again, these ethical theories are a way of framing the question to give you some firepower when you're trying to come up and argue your own answer, right? Kantianism is not saying this way is always right, but it's a way to think about a problem. That's why we study them. Okay, any questions about Kantianism? Coming back to us. Because the flip side of that was utilitarianism, right? John Stuart Mill's idea. And what utilitarianism was all about, this idea of utility, right? It's in the name. We would like to maximize the utility for this concept, for this dilemma. Which answer gives us the best utility, the most utility, right? / happiness, however you want to define utility. The most good, the most happiness, the most useful. usefulness. So the idea is when you're trying to discover what to do, you think about this utility and you want to maximize it. But you have to remember that you don't want to maximize it for just yourself. You can't be selfish in utilitarianism. You have to maximize this utility. You have to weigh it for everybody all at once. All right? And that's sometimes hard to do. For everyone, not just yourself. Okay. That's the idea. So you take here, like, maybe there's option X or option Y. You'd like count all the ways, like, it's good for these reasons. You get this much utility. You get 4 utility units. But if you look at Y, maybe if you do it this way, you get 5 units of utility, and then you choose Y, of course, right? Because it wins out. So that's utilitarianism. You want to maximize the utility for everyone all at once, not just yourself. You can't be selfish. It's also all about consequences. So you're trying to figure out what's going to happen if I were to do it this way, if I were to do it this other way. What would be the outcome? So the ends may justify the means in utilitarianism. Okay. So yeah, maximize means to maximize utility for everyone as a whole, not just you. And so the standard example of utilitarianism is, should you murder one person? If that was like, you had no option. Either murder this one person and save 50 people, or not murder the one person and then the 50 people die. But that one person gets to stay alive. So usually you do this kind of weighing. In most cases, every life is equivalent to every other life, and a utilitarian would say that, all right, I'm going to have to murder this one person so that I can save these 50 people. Okay. But again, you have to do the weighing. Like, maybe that one person is really smart and they're going to cure cancer tomorrow. In that case, maybe it's better to save the one and not murder them and let the 50 people die. Something like that. Okay? So every situation is different and you have to balance it, but that's what utilitarianism thinks. That's how you should approach a problem. Okay? And it kind of is in conflict with Kantianism a lot of the time. And so that's why you want to think about all of these different theories all at once so that you can help justify your own ideas. Okay? That's what they're all about. Any questions about utilitarianism? All right. Another big thing that we talked about that was non-programming stuff was fallacies. Remember fallacies? So when you have a fallacy, you're arguing something. It's arguments that are fallacious, right? So when you have a fallacy, it's an error in somebody's reasoning. Maybe it's your reasoning. It's an error in the argument itself, but the way that you're making the argument is wrong. That's what it means to have a fallacy. And they all have a name. Don't forget that. You can't just say, oh, this has a fallacy in it and just move on. You have to give the exact name, describe the fallacy in this class. All right? And yeah, fallacies, I'm sure maybe you've sat with your extended family this Thanksgiving and you had some debates about random things. And maybe you caught a few fallacies in those arguments, in those debates. That would be exciting. So yeah, fallacy is just when your argument's wrong. Did something wrong, you played the game of arguing incorrectly, and your argument is immediately incorrect. Every fallacy has a name, and once you notice that it's there, that argument is completely invalid from that point onwards. Okay? Pick a new argument, pick a new justification, because that sentence with the fallacy in it is not correct. Okay, so there's a bunch of different kinds of fallacies that we learned, and you learned some more when you looked up things to do your essay. Here are some fun meme examples that I found of some fallacies, and we can talk about those. But go back to the slides if you want to go and look at all of them. So here are 3 fun examples of fallacies. The first, false dilemma. False dilemma, remember, was the idea of trying to justify, like, all right, it's either option 1 or option 2, right? Those are all you get in some way. You're arguing that. It's either option 1 or option 2. You can't do anything different. But when in reality, maybe there's a third option. Okay? That's what false dilemma is all about. You're trying to argue that there's really only 2 options when maybe there's more, and so that's incorrect to do. That's immediately a bad argument. Okay? So here's the silly meme. It's like, all right, will you press the button? If you press the button, you get $50,000, but the person you hate the most gets $100,000. So this is a fallacy because it's saying, it's trying to make this claim. Either you're going to get $50,000 and somebody else gets more than you if you press the button, or if you don't press the button, you get no money at all. But I guess the person that you hate also gets no money at all. So those are the two options that it's trying to say. But the meme is like, all right, if you hate yourself, you'll press it and then you'll get $150,000. So that's the secret third option. Okay, so that's the false dilemma fallacy. Please yell at me if any of these are confusing. I'll try to re-explain them. But again, another one is the straw man fallacy. Another way to say that is like you're putting words in somebody's mouth. You're trying to claim that somebody said one thing when really they said a completely different thing that maybe sounds similar, and that's why it gets a little fishy. All right, it's hard to notice, but that's the idea. So here's silly straw man fallacy. There was a news article back at the beginning, or yeah, like a few months into the pandemic, where it was like Austria bans all gatherings of more than 5 people. And so the meme is saying, all right, if you have a family of 6 people in your house, you have to kill somebody. You can't be alone and can't be together in Austria with a large family. But essentially, this is a straw man fallacy. This meme, the joke is a straw man fallacy because it's trying to claim like this ban is so bad, even families aren't allowed to be together in Austria because of this rule. When in reality, that's not at all what the rule is saying. It's just probably outside gatherings, outside of your household, right? It says nothing about, all right, you have to drop a family member or something. That's what the rule really meant. Okay, so that's a straw man fallacy. It's trying to change somebody's argument. It's trying to rephrase it in a way that wasn't actually what they said, putting words in somebody's mouth. Right? That's the straw man fallacy. And then finally, you got the good old tu quoque, which stands for, it's Latin for you two. And I'll let you read the meme. This is just the idea of going back if somebody criticizes you of doing something, and you can just retort and say, well, you did that thing too. So what? It makes no sense for you to criticize me. When in reality, that's a fallacy. It's okay. Maybe that person did that thing before, yes, and they're trying to stop you from going down their path, right? Maybe they learned from it. So, tu quoque fallacy, just breaking out the no you or the you too. You did this thing too, so you can't criticize me kind of thing, right? That is a fallacy. You can be criticized by somebody who used to do that same thing. Not a problem. It's still correct. Okay. Any questions about any of that? Because those are the big points. If any of that was fuzzy to you, probably go back to the lectures and give them a look through. But that is the bulk of the non-programming stuff that I wanted to talk about. And I think for the rest of the lecture, I want to talk about Python, because Python is the new thing. I'm going to ask you to program and write programs on the final. And you're going to copy and paste the code into a Canvas document. Okay, so maybe practice that. But this is something I can finally ask you to do, because I couldn't ask you to really take a screenshot of like a Scratch program for the midterm. So you will be programming on the final, right? I'll be giving you Python questions. So to help you, I have made you a glorious, beautiful cheat sheet, kind of like how I made you one for the midterm. Here it is. I'll give you this in the lecture notes today. You can just click on it and see it. But let me get this on a tab by itself. Whee. Just a bunch of different features of Python that should help you make your programs as you're writing them. So if statements, like this is how an if statement executes. It's all color-coded. Here's the Python. Here's the flowchart of how it's going to execute. You got your if-else statements. Does one or the other. If elif-else statements. You have as many elifs as you want, remember. But this is kind of how it's going to work. Okay. They all do only one of these bodies ever gets run. Hopefully this diagram helps you see that. Okay. Loops. You can see the looping happen. All nice and color-coded. for loops, etc., functions. So that's going to be hopefully helpful to you as you take the final. So open that up. You'll know where it is. Yeah, let's talk about Python now. Let's see, what do I want to do first? Let's just make maybe, let's go and open up idle, and then I'll just write a very long program with a bunch of little tiny things that I wanted to talk about. So I think the first thing that I want to talk about are the types and variables. So don't mind me, please excuse me while I make a brand new folder for today and save this somewhere. I'll call this, so this is lecture 31. What do I want to call this file? I don't know. Python-stuff. But I'll have to put it in the right place. So lecture 31 folder is what I need. Python stuff program. Let's get started with it. So the first things that I want to talk about are the types. So remember that depending on the kind of thing you're using in Python, like if you use the plus, the things on the left and the right, depending on the type, the plus does different things. Same with star, right? Remember all that? If they're strings, it multiply, it like repeats something. If they're numbers, it actually does the multiplication. But I wanted you to think about your types like a cloud, right? So you got your int type. Ints are all whole numbers. They can be anything. 42. They can be positive, negative. Doesn't matter. There's infinitely many of them. But those are your ints. Ints are whole numbers. Okay. If you want numbers with decimal points, you have to use float. Floats are numbers with decimal points. Go back to that cloud drawing if you want to look at that. You got bool. Bool is a very tiny cloud. The bool type only has two things in it, true and false. Those are the only values of the bool type. And you can keep on making larger things, larger trues and falses, more complicated conditions with those ands, ors, and nots, all the ways of combining things. Okay, so let's talk about each of these. So, for example, ints. Ints are whole numbers. Variables also, you can define things with an equal sign. Be like, all right, here's an int variable, x. Set it to the int 42. And so that makes a box in memory, right? You never have to say 42 again. You can just say x, because that's what is living inside of that box. Okay? So here is my example program. X equals 42, yay. You can print x, of course. It's a function call. And that will print x to the screen. Come on, little window. There you go. That'll print 42. Everything in Python knows its type. So like print the type of x. That'll print that it's an int. Right? And then you can do number stuff with your variables, with your ints. You can do int stuff. So print, I don't know, x plus 2. Also print, comma, adds a space to things, right? Inside the print function. X times 2, x star 2, that's x squared. Those are all the kinds of things that you can do with ints. So 44, 84, 1764 apparently. But that's int stuff, right? Float stuff. If you want numbers with decimal points, you have to, the type is float. So I can make a y variable holds 3.14, and that is a float, not an int. Still makes a box in memory though, right? So I can do that. Y equals 3.14. And y here is a float, not an int. All right. So print y, print the type of y. Python knows. 3.14. It's a float. It's not an int because it has decimal places. Okay. If you want a whole number to be a float, you can add a 0.0. So like, what's the type of 3.0? That is still a float. So you can add the 0.0 if you want to start it off like that. That's one thing you can do. And then, yeah, bools. Bools end up being true and false, but the ways that you end up with true and false can be very complicated, right? So, I don't know, let's make a Boolean variable b1. It is a Boolean, its type will be a bool, so it will become true or false, but you can get at true and false in different ways rather than just typing true or false, right? Here's one way to write true, 33 less than 34. Does that make sense? This is a fancy way of writing true. Why is it true? Well, Python, whenever it sees this operation, this operand, it's like, all right, it looks to the thing on the left, the 33, it looks to the thing on the right, 34, and it asks the question, hey, is 33 less than 34, yes or no? If the answer is yes, this replaces itself with true. If the answer is no, it replaces itself with false. And so this is going to be true. Okay. I can also make b2 false. You can print that. What's b1? What's b2? Doesn't really matter. There it is. It does print true. It really was true. It became true, though. It got evaluated to true. Just like x plus 2 isn't what's being printed, it's 44 that's being printed. It's doing the math, right? It's doing this checking and then making it true and false. Right? And then you can combine your conditions. Remember your ands, ors, and nots. So what would be b1 anded with b2? Try to think about that in your head. What would be b1 ORed with b2? Think about that in your head. So this would be true anded with false, and this would be true ORed with false. What's the difference? Do we remember? Drum roll. The first one's false, and is false if one of them's false. And the second one's true, or is true if one of them's true. Opposites in that sense. Okay. Any questions about any of these types, any of these operations? Are they all coming back to us? Making variables, printing stuff. Very common things you want to do in a programming language. Okay. Let's see, what else? You have the stir type. Stir stands for string. It's a bunch of characters. It's a string of characters on like a little friendship bracelet or something. So stir, if you're using stirs, you can also use the plus operator. You can also use the star operator. You get some math-like things, but once stirs are involved, they work differently. Right? So let's look at some strings. In Python, strings can be wrapped around either double quotes or single quotes. Python doesn't care. I think the cool kids mostly use single quotes because they don't like typing shift. So I'll use that for now. Hello world, but this could have just as easily been double quotes, hello world. Python doesn't care. Single or double, as long as you're consistent. Okay. So, yeah. Print the type of S1. That's going to be stir. There it is. That's stir. And then the add, the plus on strings, S1 plus, I don't know, let's use double quotes this time, a bunch of exclamation points. It's going to build up a bigger string. It's going to add the characters of S1 to the front of a bunch of exclamation points. And so it's going to print now, hello world, and then 8 exclamation points. Or, no, 7. That's the idea. Okay? Does that make sense? So depending on the types, the plus operation does a different thing. That's important to know. And then times works. You can be like print S1 times 3. Or print, I don't know, hello, just hello times 3. You can multiply strings and by a number. The number has to be on the right, I guess. And then it just repeats that, which is nice. That's useful for some things. If you're drawing boxes or something, that could be useful. And then all strings, remember, they know their length. There's a len function built into Python that tells you, or that computes the length of any string. So print the len of S1. What is that? Oops. Apparently it's 13. There's 13 characters here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah. Alright. So that's string stuff. We're still doing alright? All the types coming back to us, all the operations on the types. The next thing we learned are lists, and lists are very similar to strings. You can think of a string as just a list of single characters, I think. That would be a good way to imagine them. Lists are a bit more general. Lists are able to hold a bunch of stuff just all together. Right? So if I make the list L and I set it equal to 2468, that makes this in memory. L. And it's just one variable that holds all these numbers at once, 2468. And you can ask for the length of a list. It'll be 4 here. You can add 2 lists together with the plus operation. And you can access and modify individual elements. You can get the 2 out, get the 4, the 6, the 8, with the indices. Remember that they always start at 0. 0, 1, 2, 3. Those are valid indices. That's how you get at these things. If you also, if you'd like, you could also go from the end. You could be like, all right, the 8 is index -1, -2, -3, -4. Okay? Whichever way that is easiest for you. A lot of people like to get the last element very easily without having to compute length just by accessing the -1 element. That's a nice thing. Okay. So just remember those indices start at 0 when you're going from the left. Right? So, all right, let's make 2 lists. Let's make L1. 5, 6, 7, 8, 9, so that's a length 5 list. If you print L1, it's just going to spit it right back at you, just all the stuff at once. It's a variable. It's holding all those things at once right now. But I could also ask Python to access individual elements. So let's ask for what's L1 at index 2. Try and guess which one it's going to print right now. Remember that the indices start at 0, so it's 7. This is 0, 1, so index 2 is the 7. Okay? And you can change things with that same syntax. You'd be like L1 of 2 equals 77. Something like that. Okay? That would work. Then print L1 now. Now it's 5, 6, 77, 8, 9. Okay? That's the idea. Lists also know their lengths. So print, let's do this so that you can all still see it. Print the len of L1. How many things are in it? There's 5 things. So the length is 5. Let's see what else. If I made another list, if I made a list L2, set that equal to, I don't know, 1, 2, 3, 4. That's a size 4 list. I can make a bigger list with L2 plus L1 or L1 plus L2. It doesn't matter. Oops. So this will make a list by combining their elements in the order in which you specified. So it's L2 stuff and then L1 stuff. So it's 1, 2, 3, 4, then 5, 6, 7, 8, and 9. Okay? Any questions about any of that? So those are the standard types, the ones that we cared the most about in Python. I guess the last thing for this slide that I want to talk about is input. If you don't want to hard code that x is 42, you want to ask these, or hey, type your favorite number, or type your name for me, please, you can use the input function. Okay? Input, when you call it, it takes as its one argument the prompt that you want to show the user while they're typing their answer, and then they hit enter and you get it. But when you use input, no matter what the user types, they type a number or their name, you're always going to get a string back. Okay, so you have to remember how to convert those types. Mathy stuff, for example, because the default, what input gives you back is just the characters that the user typed, even if they're digits. It's giving it to you as a string. Okay, so here's input. I'll call input. What is your favorite number? Question mark. And let's put a space after the question mark because they're going to be typing on the same line. It'll be a bit nicer for the user if I do it like that. There we go. And so we're going to call this input function. It's going to show me this prompt while I type, and I'm going to hit enter. And the result will go inside the num variable. So I can print num. I can print the type of num, right? And then maybe I want to give back that number times 2 or something. So there's an issue right now. There's no conversion happening. Let me show you. So what's your favorite number? Let's type that our favorite number is 42 and hit enter. And so 42 is going to go into the num variable. But 42 is a stir. Everything that you get back from input was a string. Okay? So if I print num times 2, I'm going to get 4242 out, which is absolutely not what we wanted. Right? So if you would like to do number stuff, if you expect the user to type a number to you, and you'd like to do number stuff with it, then what you need to do is convert it. You can say like num equals the int form of itself, int num. If you use the name of the type you want, like a function, it will convert something to that type. All right? So int num makes the integer out of the num variable. And then we put it right back into the num variable. Okay? So now it's type, print the type of num. It will have changed to int. And then if you print num times 2, it'll finally do what you wanted it to do. Okay? So what's your favorite number? 42. Here, after I converted it, now it's an int. And then num times 2 is, of course, 84 when it's an integer. Probably that's what we want. Okay? So this line is saying, now, num is an int after it's finished. Okay? So that's the conversion right there. Any questions about that? So input, it's a way to get stuff from the user. You're always given a string back. If you want to do number stuff, you got to convert it to a number. Maybe an int, maybe a float. It's up to you and your program. All right, we good with all that? So that's a bunch of straight line code. Let's get into branches if we're still doing all right. So let's see what I want to talk about. Yeah, a few more slides for the day. Let's talk about our if statement. So it's a way to do one thing or another, potentially multiple, pick from multiple different possibilities, multiple different options with elif as well. But let's go through that. It's a way to branch. This is branching, conditionals. So usually in Python, you want to do one thing or another, and you have to figure out, like, okay, which case am I in? So you have to compare. You have to do your comparisons, check for something less than something else, something equal to something else. So remember all of your equals, not equals to. It looks a bit weird. It's an exclamation point and then an equal sign. But that's how it works. And then less than or equal to, just put the equal sign after it, and so on and so forth. Again, you put two things on each side, and it's going to either give back true or false. Okay? So usually, you want to do something like this. Like, you've got two variables, maybe both from the user. You want to look at them, compare them, and maybe if x was less than y, you want to do thing 1, and if x is not less than y, if that's a false statement, a false comparison, if that's not true, then you want to do some option 2, right? Also, just as an aside, if x is not less than y, if that's false, that means x must be greater than or equal to y. That's a good thing to remember. So yeah, you can ask Python to figure out the answers to these questions and do one thing or another, or potentially multiple things, with conditionals. All right? Don't forget about the indentations, the colons, the indentations, all the bodies and stuff. But this is how an if statement works in Python. It's like if, then you give some conditionals, some conditional statement, let's say cond, something that becomes true or false. Then you put a colon, and then you tab over. Idle will do it for you, right? You tab over, and then you write the body of the function indented. You can make it as long as you need it to be, execute as many lines as you need it to execute, and that will always be run if that condition is true. Okay, that's the idea. That is what if is all about, and if you go and check this pretty cheat sheet, that's what it's saying, right? So you got some straight line code before and after, so you're running before, but the if statement works by checking its condition. If it's true, it runs the body, and then it continues to the rest of the code. Otherwise, if the condition was false, it just skips over the whole thing. No body executed at all. Okay. That's different from else, if else, so it checks the condition. If it's true, it does the body of the if. If it's false, you have the else case for that case. If it's false, it runs the body of the else. And then it, of course, runs the rest of the program down that's unindented. Okay? So here's my first example. Let's make a program that, like, I don't know, it checks, we pretend we're at an amusement park, and it's going to check to make sure we're tall enough to ride the ride we're about to go on. So we're going to get some input from the user, like ask them for their height and check if it's like at least 4 feet tall or something. Then you can ride the roller coaster. Okay, let's ask the user for their height. So let's make a new program. I'll call this conditionals.py. Do that. Let's ask the user for their height. And so I'll say input, enter your height in inches, colon space, so they have a nice pretty place to type it. And then we're going to get this back from the input function. And we should definitely save it away somewhere. Height equals input, enter your height in inches. And now we have a question to ask ourselves as the programmers. Like, what do we want to get back here? Like, we're going to compare the number. Do we expect the user to type always a whole number of inches? Like, or is somebody very, very precise about their height? Like, I am 5'10½", so I am like, I don't know, I am 55.5 inches, because we're going to have to convert it to a float if they're going to do something like that, right? Otherwise, we want to convert it to an int. Let's pretend that the user always gives us a whole number of inches, okay? And so let's convert it to an integer. Just put it on the same line if you'd like. So now we have a number, and we can do number stuff with the height variable. Okay. If height is less than 48, then you can't go on the ride. Print, sorry, you can't go on this ride. Sad face. Else, that means the height was greater than or equal to 48. Then we'll say, all right, you can go on the ride. Single quotes for this string. Happy face. Okay? Exclamation point as well. So this is how we run it. So we're going to ask the user for their height in inches. I don't know. Let's say they're 42 inches tall. It's going to hit the true branch because 42 is less than 48. Sorry, you can't go on the ride. If we rerun it and type that our height is at least 48 inches, so if we type that it's exactly 48, it'll be like, you can go on the ride. And if we type anything bigger than that, it's still going to be, yes, 49 inches, you can go on the ride. Okay. So it's always one or the other. This is the body of the if, this is the body of the else. Only one of those is going to get run. Okay, and you can make it, you can have as many lines as you want. Maybe you want to print out multiple things. As long as they're all indented, you can have as much as you want up in there. Okay, any questions about if-else statements? It must be this tall to ride. So that's the first simple example. Let's get a bit more complicated. Let's do a grade calculator. Let's have the user enter a grade, and then we'll tell them, or we'll ask them, once they type it, what their grade was. And we'll tell them that. So this is going to bring this idea into play. Like, either something's true, and like the grade's an A or something, or it's false, and okay, it wasn't an A, but maybe I need to check for B and C now. All right, it's true, and then it's a B. If that was false, now I need to check. Okay, that was the check for is it a B case. Let me now check for if it's a C case, and that can be a very wide little branching factor down there. So you can make these flowcharts a bit wide when that happens. So we're going to need to use a lot of elifs for our grade calculator. Is the idea. We're going to have a bunch of different options, right? We want to print either, like the user gives us their grade, either it was an A, that could be condition 1, or it was a B, that could be condition 2, print B, or it was condition 3, we'll need another elif for it was it a D, and then our else could be, all right, if it wasn't A, B, C, or D, then it was an F, and we'll type. Okay, so we're going to do an if elif else with quite a few elifs, okay? But the idea of these statements is that it's always just one condition, one indented condition is ever going to get run. It's just the first one that works. So the very first thing that's checked is condition 1. When we hit this if, elif, else, if it's true, we run the body of the if, and then we're done. We we go straight to the end. Nobody else gets considered. We're just finding the first thing that works, and then we're done. Right? But if this one was false, if condition 1 was false, then we move on and we try this one. And potentially the rest on down the line if that keeps being false. But if that one was true, then we'll use its body. We'll execute its body, and then that's the whole thing. Then we're done. We're done with everything else. We skip over everything else. If that's false, then we follow through, right? We try a few more LFs if there's more, but if it's an else case at the end, then we run its body, and that is the end of the whole thing. Okay, so it's always just one option gets run. That's the idea. So let's write that program. Let's ask the user for their grade as like a percentage, a number between 0 and 100. So grade equals input. Enter your grade as a percentage, colon space, and what should I be converting this string to? Because if I just use input, it's a string, right? What's the right type to convert to for grade? What do we think? The default's definitely wrong. Can't be a string. Can't compare the string 99 to anything useful. I could use int, yeah. Are there any other options though? Yeah, there we go. Why float? Yeah, you could have gotten partial credit, something like that. Usually, you're going to have a grade that involves decimal places. So it definitely should be a float. Nice. Because maybe your grade's like an 88.5. You want to make sure like it's all there. Something like that. So it should be a float because there's probably decimal places in the grade. Okay? And now, the calculation's pretty easy. We just make a big if else, and we make sure like we're always checking for one thing at a time, A, B, C, D, and F in that order. You could do it backwards as well. But this is one way to do it. So let's have the first part check if it's an A, if the grade's an A. So if grade is greater than or equal to 90, 90.0 if you want to be extra fancy, but just 90 will still work, then that was an A. Between 90 and 100, or maybe it was more because they got extra credit, but the grade is an A in that case, right? Otherwise, you can read LF as otherwise, that's how I like to read it. Otherwise, maybe it was a B, right? Otherwise, maybe it was a B, maybe it was a C, etc. LF. Because, all right, if this was false, grade is less than 90, but I'm still not sure if it was a lot less than 90 and it was an F, or it was just a little bit less than 90 and it was a B. So we need more conditions for that. So grade, if it wasn't greater than or equal to 90, we always know if we got here that it's less than 90. But maybe if it's bigger than 80, that means it's within 80 and 89.999, and then it's a B. You see that? Because the only way we got here is if this was false, we know that the grade is smaller than 90, and if this is true, it's bigger than 80, so that's our B, that's our range, between 80 and strictly less than 90, because that's the opposite of that. All right, if that wasn't true, otherwise, if the grade is greater than or equal to 70, then we know it was between 70 and 79.999, because if it was bigger than 79.999, it would have hit the B or the A case, one of the two. If it's neither of those, we didn't have any of those work yet, we know that it was a C. Does that make sense? And the order really matters here, because if I checked for 70 first, it would think that everything is a C, right? Because a 90 is bigger than 70. You do want to do the least likely thing first, the hardest thing to make true first. Otherwise, it would mess things up. LF grade greater than or equal to 60, then it's between 60 and 69.9999 forever. Print D. And then otherwise, if none of that's true, none of these conditions was true, it tries them in order, they all failed, they were all false, it must have been smaller than 60 and it was an F. Okay? So that is the grade calculator. I don't know. 55, enter your grade as a percentage, 95.5. There's your A, 82.1. Oh, sorry, that was not the first one. See, that's what goes wrong if the user tries to type a float. enter your height in inches. Sorry, 42. And that was 82.1. Okay, that's a B. So on and so forth. We'll do like 55.555. The grade was at F because it falls through. All right. So, are there any questions about this program or anything else? Is that making enough sense? All right, let's keep on trucking then. Let's do some loops. A. So the simplest kind of loop is a while loop. And what a while loop does is it allows you to come back to your condition. This is how it works. It says while condition colon, you have your body, and you're going to repeat that body as long as the condition is true. As long as the condition is true, you're going to keep coming through, rechecking the condition, executing the body. The whole point of a loop usually is to eventually stop. So the body is going to do something that's going to eventually cause the condition to become false. And once it does, then you're done with the loop. All right? That's the idea. That's loops in a nutshell. So, for example, if we wanted to print all the numbers from 1 to 10, here's how we could do it. Start some some variable. Usually you call it I in computer science. Start it at 1, and then you have a loop. You continuously loop and print I as long as I is like one of the numbers that we care about. As long as I is less than or equal to 10, then, all right, if that's ever true, we want to print I. I'll print the 1, the 2, the 3, as long as it's less than or equal to 10. We want to print I. And then we also want to increment I. Make it, if it was 1, we just printed the 1. We wanted to print 2 next. So increment that I, make it 2 now. And then we want to always come back to this condition. Okay, it's 2. Print the 2, increment it to 3. Okay, it was 3. Still less than or equal to 10. Print the 3. Make it 4 so that we print it that way next time. And then finally, it's going to be like, all right, I is 10. 10 is less than or equal to 10. Print 10. Make I 11. Oh no, 11 is bigger than 10. That's false. Then we continue with the rest of our program. We do that after part. We do the rest of the code down here, if anything. Okay? So let's do that one. And we can copy this flowchart to code pretty quickly. Let's make a new program for it, though. I'll call it loops.py. Alright, so let's start I at 1. It could be any variable name you want. Call it X, call it hello. Start I at 1 while I is less than or equal to 10, colon, indent everything that you want the body to be, print I, then increment I. So I equals I plus 1. 1 more than it used to be. And that will eventually cause it to print 1, 2, 3, all the way to 10, make I 11 at the very end, and that is what will stop this loop. All right, so that gives me the 1 through 10. Are there any questions about that? Is it all coming back to us? And you can, of course, change the range. You could count only, you can make it start at 2 and only output even numbers, start at 1, increment by 2, and only output odd numbers. You have a lot at your fingertips there. A useful thing inside of loops, potentially, that you may care about is break. If you ever want to stop early inside of a loop, you can say break. Just for your knowledge. Let's say, like, all right, really, we're looping from 1 to 10, but actually I think we're done at 8. So if a very simple way to have it stop after we've hit 8 and printed 8, or I guess 7, because we've just made 7, 8 on this line. If I is equal to 8, you can just say this line, stop early with break. Just say it on a line by itself, break. And that will stop the loop. So watch what happens now. It goes from 1 to 7 only now, because printed 7, made 7, 8, I is now 8. Okay, we apparently don't like the number 8, so we break, and that stops out of the loop. So that's one way to quit out of a loop if you ever need to. So that's my first simple example. Are we ready for a fancier one? Any questions about the first one? All right, so let's take a bunch of numbers from the user. So let's have potentially an infinite loop. The user needs to eventually type -1. That's going to be the game. The user is going to type a bunch of numbers, and we're going to sum them all together until the user types -1 as their number. We're going to pretend that -1 is not any number that the user cares about adding. That's going to be like a marker to tell us when we're done. So here's what the user might type: 42, 43, 44, 1, 2, 3, and then they type -1. What we should have done is read all these numbers and then notice like the -1 that stops us, and then add them all together and output that sum of those numbers, not including the -1. The -1 is just telling us when to stop. Okay? So that will require a fancier loop. So the user is going to type a bunch of numbers. We need to keep track of their sum. So let's make sure that sum is sticking around in a variable. Keep track of the sum in a variable. So sum, or I guess let's call it total. Total equals 0. That's how I called it last time. And so we want to repeatedly get a number from the user and keep on adding it into total as long as that number was not -1. And that can be translated pretty quickly to Python. As long as would be our condition, right? Enter the next number or -1 to stop, right? And so let's pretend we're only getting whole numbers, so we're getting ints from the user. Next num equals that. And so do this while next num is not equal to -1. Here's what we need to do. So every time we got a number from the user, we need to add it into total, add next num into total, and we should get the next number, because we want to get as many numbers as the user wants to type until they type -1. If we're in this body, we didn't get -1. We don't want to stop. We just need to get another number. Maybe the user is going to type -1 this time. Get the next number. Or maybe they want to type 100 more numbers until they type -1. Okay? So add next num into total. We can say total equals what it used to be plus next num. And then getting the next number is as simple as just copying and pasting this line all over again. Okay? And so this loop is going to stop once the user types -1. Either they typed it and we didn't even do the loop, or they typed it here, and the total is the sum of all the previous numbers. Okay? And that will stop our loop, because when it's equal to -1, this not equals comparison is false, right? It only continues while it's true, while it's not equal to -1. So once it's finished, what do we know about the loop once we get to the outside of it? So if we get here, when we get here, assuming we do, the user eventually typed -1, right? The only way for us to stop this loop, there was no break. When we get here, next num must be -1. That's the only way. That's the only thing that got us out of this loop. Next num being -1. Output the sum. That's the last thing that we need to do. Print, I don't know, sum colon space, and then total was the variable we were keeping our sum in. And so here's how we can do it. We'd be like, enter the next number, -1, 2, 3, 4, 5. All right, that's enough. -1. Give me the sum of all the numbers from 1 to 5. The sum is apparently 15 from all of those. Okay? That's the idea. And you can do this as much as you want. Add 5, 5, 5, -1, so that's again 15. You can immediately type -1. The sum of all the numbers, when you type no numbers at all, was 0. Yeah, that is the idea. So continuously get any number from the user and add what you just got into your total while the user has not typed -1. That's what stops us. Any questions about that example? So I got one more slide for us, if we're doing okay. All right, let's do for loops. Back to the cheat sheet. So for loops are a way of iterating through something. Usually you think of it as a list. Just any iterable thing. Think of it as a list, though, at least in this class. So a for loop, you write a little special variable and you say in. For some name, some variable name in some list, or some iterable thing like a range, you run the body with var set to the next element in that list, or that range, all right? So here's kind of how the loop works. Python asks the question, is there another element in list that we haven't gone through yet? If there is, then it sets a variable to that next element. Maybe this is the first element, if we haven't been here yet. We run the body with variables set to that element, and then we come back and we say, all right, is there a second element in the list? If so, set the variable to that. Run the body now. Keep going in order through that list, and eventually there won't be anything left to go through. We've iterated through everything. We've visited every element. At that point, the loop is done. We can do whatever is below. All right? So that is for loops in a nutshell. Let's talk about those. So for loops, yes, they iterate through something, usually a list. Range is a good way to make a list-like thing that goes through some numbers. So range 50, for example, holds 0, 1, all the way to 49. It's always one less than its ending element for some reason. But yeah, any list is something that you can iterate through, like visit all the elements, 1, 2, 3. Sum them all, print them out. Range 50 is essentially the list. Let me draw this better. Range 50 is the list. This becomes the list 0, 1, 2, all the way to 49. And so, yeah, with that in mind, let's do some fancy examples. First fancy example, let's find the minimum of the values in a list that the user enters. So let me type this up, and let me show you an example of how you do this, first of all. The way that you find a minimum, it's kind of the opposite of the way you find a maximum. But here is, let's say this is the list L that I want to go through and find the minimum element of. Here's the algorithm. You make a guess. You pretend that the first element in the list, the 0th element, pretend that that's the minimum. Just so, say 3 is the minimum. And then you go through the list from left to right, and you update your guess. Next, you look at the 1. You're like, all right, how's the 1 compared to my current guess for the minimum? Oh, it's smaller. So the minimum, it would be a better guess to put 1 in here. And then you visit the 2 and like compare that to your current guess to the minimum. Okay, 1 is smaller. I'm not going to update it. I'm going to keep it that. And then once you've visited every element in the list, updating your guess when you find something smaller, you found the smallest thing. You must have, if you think about it long enough, you must have placed the smallest thing in the min variable. All right? So that's my fancy example for this. So we can use a while loop to fill up a list. This will be fun. Watch. Let's get a list that the user enters. Let's call this for loops.py. And so let's set a list to emptiness, and then we'll add one element at a time to L. Fill L with numbers that the user enters. So this will need a while loop, but it's essentially going to be this idea all over again. Get some numbers. Boop. -1 to stop. So add the next number into L is all. So this will add L equals L plus the list containing just next num. This is me copying our code from before and creating a bigger list with it. So L gets to be larger and larger each time. Definitely come back to this code. This is a fun example. It's a bit complicated though. Enter the next number, -1. So 1, 2, 3, 4, -1. Oh, sorry. I didn't press shift properly. My bad. L equals L plus next number. Not equals, L equals. 1, 2, 3, 4, -1. And so that will keep on adding one element at a time to L. And now the list holds 1, 2, 3, 4. Isn't that fun? And you can do this as much as you want. 42, 43, -2, -1. So now that list holds 42, 43, -2. So now I've just made a list with a bunch of the things that the users typed, so I don't know what's in there. And now I want to find the minimum element, whatever it is. All right? So I follow this algorithm. I make a guess for what minimum should be, and make a guess that the first element's the minimum, and then I loop through the rest of the list and try and fix my guess. See if I find a better guess for the minimum now. So make a guess that the min is the first element of the list. Min equals L of 0. That's my first guess. That's the first element of the list. And then you loop through. I guess you don't have to ever visit the first element again, but it's easier to use a for loop and just go through everything. Loop through every element of L and update our guess. All right, so for, call the variable x, for x in L. So this x gets a chance at being every element of the list L, and L is what the user type. We have no clue about what it's there. What we need to do is for every element that we see, if x is better than our current min, if x is a better guess for the min should be set to x. That's the idea. That's how it needs to work. Okay? In that case, if x is less than our current guess for the minimum, then x is a better choice. Min equals x. Right? And so once we've visited every element of the list, updating our guess for a min if we find something smaller, we really have found the smallest thing. Min holds the true min now. Right? Print min colon space min. I don't know. 3, 1, 2, negative 1. And it found that the min was 1. It doesn't matter where the min is. It could be the first thing, could be the last thing. 1, 2, 3, negative 1. It correctly finds that the min is 1. 3, 2, 1, negative 1. Even if it's the last thing, it finds that the min is 1 no matter where it is. And this will work for any list. Isn't that fun? It's a neat little idea. Fun little algorithm. Is that coming back to us? Any questions about that? So I've got one last example. Dun, dun, dun. So, my last example. If, remember that one thing that you might want to do when you're iterating is you might want to go through a bunch of numbers and figure out, hey, is this theorem true or not? You can prove a theorem with a loop by trying a bunch of numbers. So here's a theorem. There exists an x such that x is between 32 and 37 and x is prime. So this is a statement saying there exists an x between 32 and 37 that is prime. This is the mathy way of saying that. And we'd like to prove or disprove this statement. The way that we can do that is iterate from 32 to 37, try all the numbers in between, 32 through 37, and check if any of them are prime. If we found one, that could be our x. Like maybe 37 is prime, I don't know. Then that is a witness to this proof being true. Otherwise, if none of them are prime, then we have disproven that theorem. It's false. Okay, does that make sense? So let me quickly write an isPrime function. Don't worry too much about this. I won't ask you to write an isPrime function on the exam, but this is just going to be a function that takes a number and outputs whether or not it's prime. So def isPrime. The way to check for primality, not that it matters, is you try every number for n in range 2, because that's the smallest prime, 2 to the, you can go all the way up to num if you want, but technically you can stop at, you just want to find one factor. There's guaranteed, if there are any factors, it's between 2 and the square root of that number. To the 0.5 power plus 1 to worry about some rounding issues. But yeah, if you found a number that goes into it, num mod n is 0. Again, don't worry too much about this. This is just to get the example to work. Then I found a factor, return false. Otherwise, if I've gone through every possible factor and I haven't found any, return true, that number really was prime. Okay? So I can use my isPrime function now to prove this theorem. So let's find an x such that it's between 32 and 37 and it's prime. So we'll prove this theorem by, all right, let's iterate. Let's iterate through every number. For n in range 32 and 38, remember, because it's got to be one, always one less than the end. This will iterate through 32, or iterate from 32 to 37. Come on, of course. If we find that n is prime, if is prime n is true, then print the entire statement was true. We found an example. We found a number between 32 and 37 that's prime. That's how you read that. Print n is prime. One, two, three, -1. And then what do you know? The statement is true because 37 is prime. We found an example. We found something to be x, such that it's between 32 and 37 and it's prime. That's how we wrote the program. And so that is converting from math to code and proving a theorem with Python. That's one last example of for loops. Okay. Any questions about any of that? Definitely go back and study that. These are fun little examples. But I think, check out the cheat sheet as well. I'll release that today on the, just click this link. It'll be there. But yeah, that is everything that I wanted to talk about today. We'll come back next time and review some more.